right, good morning. So looks like we got people on Discord. One person is on YouTube. Excellent. This is our last lecture. And then we have the final exam on Monday. Monday is our final exam, and I think I put it into the class calendar so that way, we won't forget. I won't forget. Alright, so there you go. Final exam is on the 16th, and the start time is 12:45 p.m. and it's a 2-hour exam for the final exam. Alright, thank you. Thank you, Philip, for confirming that. Yeah, I'm one of those people, where I cannot remember whether I locked my car or not every single time, so I have to go back and, kind of beep the car a few times. Not that anyone would actually want to steal my car, but actually I should put it in a slightly different way. Not that everybody can steal my car. It's a stick shift car, so that means some people may not be able to drive away that car. They can push it away, they can put it in neutral and just push it away. Alright. That's right. I'm pretty sure, at some point, we'll have, an application to kind of make use of proximity, not sensor, but proximity detection. So if you are, so many feet away from your car, it just kind of automatically locks itself. I mean, it kind of makes sense, right? Yeah, I'm not sure about Kia. My daughter has a rental Kia right now. It's a Kia Soul. As far as I know, it doesn't have that feature, but it might have that feature, and I just did not know how to activate it. It does have some other cool feature, like if you're backing out of a parking space, there's a sensor to tell you whether there are cars approaching you from both sides. So that's actually pretty useful as a sensor. I mean, there are times when I go like, oh man, is there a car coming? Because I can't see it, right? But coming from Hong Kong, I'm actually used to parking backwards. So I park tail first into a space, especially those perpendicular spaces. So this way, getting out is easier. But sometimes I can't do that if there are too many cars around me. All right. So we got about a minute and 20 minutes to go. And then today's focus is going to be the A-star algorithm. I would just basically say, even though we are using A-star algorithm, it's the technique that counts. Okay, can we follow the algorithm going in one direction? And can we use the trace or partial trace of running the algorithm and go back and reconstruct things as much as we can? As Chris already said in a previous discussion, it's not always possible to reconstruct the entire graph because there are vertices or there are edges that we may not know because if they are not reachable or they're not on the optimal path or for whatever reason, okay, they're not touched, and as a result, they don't show up in the trace at all. But we'll try to do it as much as we can, right? We'll reconstruct the graph as much as we can. That's kind of the question 2 from the exam last semester. But as I said, don't get too fixated on the A-star algorithm. Instead, learn the technique, not so much the process. So I think that is really kind of important to understand is, I emphasize on the technique generalization much more than the process itself. Because anything that has a set process, is already automated. They don't need people to perform tasks where the process itself is very predictable, it's very linear. So that's kind of my point here. All right, it is time to get started. I am going to get started. So we'll start with the A-star algorithm homework, and then we'll move on to question number 2 of the exam from last semester. All right, so the first thing we need to do is to copy the question description um, into into the spreadsheet. That's right. Okay, there we go. No, we cannot have any extra time because that is by contract. We get 2 hours and that's it, because the final exam schedule is published ahead of time, which means some people may have scheduled other things around the final exam time, and as a result it would not be okay to extend the final exam time. Yeah, so that's pretty much that. All right. All right, so let's go ahead and go back to our spreadsheet. Um, and we'll work on this particular algorithm. I'm staring at this, because because of the way I use the equation, it doesn't break up the definition of D from the definition of H. So I suppose this is one way I do it. I can do a screen capture and just kind of copy and paste it into the spreadsheet. That's a really lazy way of doing it, and obviously not very accessible. But as far as I know, no one in this class requires accessibility. So I'll just go ahead and kind of cheat this time. Alright, so click Save. And I think I have the spreadsheet open somewhere. Let me look for that. A-star, there we go, A-star trace. In fact, I have 2 tabs open for that. Alright, so we got the bitmap, and we're gonna paste the bitmap, let's just say somewhere around here. So this is the description of the question. Okay, it's unique to this semester. Last semester, there's a different graph. And I'm just keeping an eye on the text channel. Will we have one of these algorithm tracing on the exam? I do not know. You guys keep asking me about things about in the future that I have no idea about. No, I really do not know. I'm not just saying that to upset people, but I really do not know. I really have not come up with the questions for this semester yet. But one thing you can almost know for sure, that's one thing you know for sure, is it's not going to be the same as the previous semester and typically any semester prior to this semester. So that's basically what I do. I don't want to reuse questions because that. I mean, some people collect past exams and answers to all the past exams, and I just don't see any points in reusing questions then, because then those people would just kind of be able to look it up and go like, oh, okay, I see the answer to this question is this and so on. So I don't do that. All right. So okay, that is a very legitimate question. Trying to figure out how to properly prepare. All I can say is you have to understand the concepts and be able to apply the concepts. I'm not sure whether this is a good analogy or not, but I'm going to use it. When I was a high school student, physics was one of the subjects where I have to take the high school exit examination on. And me and my classmates, we study in a very different way. My classmates would purchase additional textbooks, exercise books, and whatnot, and end up with a pile about yay thick, and they complete every single question in all the practices. I did not finish the questions in the textbook itself. And that's because most of the time I'm spending the time to actually understand the concepts and not to memorize the equations. So if you remember physics, because I think some of you probably have to take physics in order to complete your transfer degree. I think most of you probably do not. But anyway, in physics, there are some very fundamental concepts like, velocity is the change of displacement over time, that sort of thing. So I can only remember the most basic equations, but not the more complex equations like this is the height, this is your gravity, and how long does an object take to get from that height onto the ground. I cannot remember those equations. Even to date, I cannot. I have to re-derive everything from the most elemental equations. So in the end, I got the same grade as all of my classmates. Um, so what I really want to say is, it is about really understanding the material to the point where you are able to apply what you have learned, or apply the knowledge in order to solve the problems. So I really kind of put a lot of focus on that, in not only in this class but in all the classes that I teach. I obviously there are people who disagree with this, but I think in computer science, this particular aspect of how to teach a class, I think I think it is important. It doesn't mean that everybody has to agree with me. All right. So anyway, getting back to the trace here. So the trace is about following the algorithm. In other words, you probably really want to understand the algorithm itself and what it is expressing. Okay, so that's really that's like first step, right? Because if we misunderstand or do not understand the algorithm, there's no way to go forward, which means to trace the algorithm or the behavior of the algorithm correctly, and forget about going backwards. Looking at the trace and go back to reconstitute the original graph. So having a really solid understanding of the algorithm and how algorithms work in general is really important. All right. So we're going to get started here. The way we initialize G, so the first thing is not really just to say, okay, I vaguely remember tagging class, did da 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 with the G and the F values. No, you really want to ask, what is the G value representing? What is the F value representing? Okay, because that associates a meaning, semantics, to the symbols, and I think that really is important. So the G value is basically the length of the shortest known path from the start vertex, which in this case is vertex A, to whatever vertex of the G value that we are trying to figure out. So in this particular question, we know that the start vertex is vertex A and the destination is vertex X. So it makes sense that the G value of A is going to be 0 because the length of the shortest path from vertex A to vertex A is 0. That really just kind of makes sense. And then everybody else is going to get infinity because we really have no idea whether there really is a path to get to those vertices or not. So when the G value remains as infinity, it basically means we have not found a path to get to that particular vertex from the start vertex. So if that is the meaning of the G value, what is the meaning of the F value? So the meaning of the F value is the length of the shortest, the estimated, okay, let me add that really important word here. The estimated length of shortest path known up to this point from the start vertex through a specific vertex to the destination. So one part of it is known, the other part is projected based on the heuristics. Okay, and we got a question here. I got confused on what the destination is supposed to be. I did not read the whole question. Okay, so here's the question. The question says the destination is vertex X. So that part is also important. I mean, with the homework, obviously, if you did not get it all right, you get some points taken off. But all the homework assignments add up to 20% of your grade. In other words, if you kind of mess up a little bit on one particular homework or even a few homework, I mean, it's going to cost you some points, but it's not going to be very significant. But when the same kind of mistake is made in the final exam, it can be very costly because the final exam itself, all by itself, is 40%. So if let's just say that we have 4 questions. I'm not saying that we are going to have 4 questions. I'm just saying that if we have 4 questions, each one is 10% of your final grade already. So I would say in the final exam, just spend that extra time to read the questions carefully. Okay, just read it really carefully. And if you don't understand something, if you need clarification, text me. Okay, so I can help you understand what the question is asking. Now, that being said, I cannot answer questions about the material in the class. So, for instance, if somebody point to the A star algorithm on a particular line and ask, I'm not really sure what this means, the for all thing and then blah 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 blah. I cannot explain that during the final exam. Okay, that is something I cannot do. But if people are asking, so what do you want in the answer? Do you want the answer in actual numerical value, or do you want it in the equation? I can answer that one, okay, because that's about what the it's about the format of the question of the answers to the question. It's not about whether you understand the material or not. So I just want to make it very clear, of what you can expect when you ask me something during the final exam. All right, so I know some people are still typing, but I'm going to go ahead and work out the values of the everything. So, all right, there we go. It does say vertex D is the destination in the assignment, and then below it says the destination vertex is X. Well, there's no vertex D, so I mean that really leave behind just vertex X being the destination, the bitmap. The bitmap. That is from the previous exercise. Remember last time, when we talked about this, I distinctly said, one part of this is from last time, and then the other part is for the actual. Okay, let me check what it does look like. Okay, because I don't want to be, because I remember that I kept. No, that's it. Alright, so some of you might have opened this before I make the change. But in the class, I did specifically say that, we use the old one to go over, and then the new one is down here, and I'm going to change it so that it would appear up here. So I'm pretty sure I said that. Now, obviously, I can go back to the video recording of the lecture and find out, but I'm fairly certain that that's what I said. Alrighty. Alright, so Nathan is responding to the question of what is f. So f is basically the estimated length of the shortest path from the start vertex through a particular vertex to the destination vertex. So f of a is going to be just the heuristic value from a to x, and according to how we define h, it is just 0. So we put a 0 here, and then for everybody else it's just infinity, because it is adding something to g of x or g of whatever vertex. So that means it's going to be greater than or equal to the g value. So if the g value is infinity to begin with, all of these are going to be infinity. Previous are all initialized to unknown, because this is basically how we can track our way back from the destination vertex back to the start vertex, so that we find the actual shortest path from the start vertex to the destination vertex. So that's how we initialize G, F, and Prev. And then for O, uppercase O, it is initialized to be the start vertex in this case, which in this case is vertex A. So the A is the only element in O at this point. So if you're doing this, if you're watching this, you probably want to open up the algorithm on the side, so this way you can look at the trace and the algorithm at the same time. I don't need to look at the algorithm, because let's just hope that I know what I'm talking about and understand the algorithm, to the point where I don't need to refer to it. Okay? All right. So the next thing we need to do is to choose a vertex C. Oh, wait. Okay, this is important because we are not quite there yet. We have to evaluate the condition of the while loop and determine, are we good now? I mean, can we just kind of leave now because we are done? So how do we determine whether we are done or not from the perspective of the while loop? Now, this is really important because I have seen some people not understanding the condition of the while loop and perform additional iterations when it's not needed. It's not specified by the algorithm. So how do we determine whether it's time to go or not? I mean, you can just read from the algorithm, but it's giving you a quantified expression, so you kind of have to translate that into a more colloquial or casual description. Okay, so that's good. Okay, what Elijah typed in the text channel is a good starting point, but it is not quantified. Okay, so it really needs to be quantified and say if every element in O has an f value that is greater than or equal to g of x, then we're done. Okay, that is really, really, really important. Okay, because just also specify, so all is good, because if you just say, when v is in O and v satisfies this requirement, are we talking about just having one single element in O that satisfies this requirement and we're all good, we are ready to exit the algorithm? Or are we talking about every single element in O has to meet this requirement in order for us to get out of the loop? So that part is really important, because not clarifying the quantifier can lead to two different outcomes. So it is for all in this case. All right. So what is it in this case? I mean, can we exit now? Well, let's take a look. The only element in O is vertex A, and if we look up f of A, it has a value of 0. If we look up g of x, it has a value of infinity. The question is 0 greater than or equal to infinity? I don't think so, right? Okay, so we get into the while loop, and then inside the loop, the first thing we do is we find a vertex, or we find an element in O such that it has the least of all the f values among the other elements in O. Well, this time, it's not a big deal because we only got one element in O, so there's nothing to compare to, so we have to choose A as variable C. So there we go. And once we remove a particular element out of O, we have to get it, we have to remove it from the set too. So now we look into the outgoing edges from vertex A. And there are 3 outgoing edges from vertex A, because we can see here. You can find that from the D description, because you can also find it from the E description, because they are. The D description just basically adds a distance as an integer, as a real number, compared to the edges, which just describes the connectivity between the vertices. All right, so A goes to B, A goes to C, and A also goes to X. Now, the order of going through those edges is not important, so you can choose whatever order you want. You can start with AX and then go back to AB and then go to AC. It doesn't make a difference. So we are going to kind of randomize a little bit here. We'll go to AC first. Okay. So if AC is the first outgoing edge from A that we are considering, then we have to compute the value of the local variable t, which is g of A plus the distance from A to C. G of A is 0. And if you look at the D function, from A to C is 5. So 0 plus 5 is 5. So t is 5. And then what we do is we compare t with the g value of vertex C, because the g value of vertex C is telling you what is the length of the shortest path currently known from the start vertex to vertex C in this case. What t is representing is the length of another path, going from the start vertex to vertex C also. So when you compare these two numbers and t is less than infinity, that means we have found a shorter path from the start vertex to vertex C. So as a result, we update the g value of vertex C to t, so whatever t is, which is 5 in this case. But we also have to update the f value to be the g value, which is 5, plus the heuristic from C to X. So the heuristic from C to X is 0, so that means the F value is also 5 in this case. And then we have to update the previous, which basically is trying to remember how do we what using the shortest path. Okay, how do we get to vertex C? What is the immediate vertex right before vertex C? And the answer is it's going to be vertex A. And because we just changed a bunch of stuff about vertex C, we also have to add C to the set of O. So that's basically what we do for one iteration of the for each loop inside the while loop. All right, so let's move on to the next one. We can use B, we can use X. It doesn't really matter which one. I'm going to use X here. So in this case, we are trying to compute t as g of a plus the distance from from a to x. So the distance from a to x is 10. So this is basically just a value of 10 here. And then we compare this 10, which is the t value, versus the g value of x. And the g value of x is still infinity. 10 is greater than or equal to 10 is less than infinity is true, so that means we have found a shorter path, so we update that. And we also have to update f of x. F of x is easy. It's just going to be the same as the g value, and that's because x is special in a certain way, because x is a destination vertex. And to get there, using this quote-unquote shortest path, or the shortest known path up to this point, we have to go from A. So that's why we update that with A. And since we just updated a bunch of stuff about X, we have to add vertex X to the set O as well. All right, so let me go back to the text channel. Oh, okay, never mind. I thought, okay, that's coming from my other class. Okay, never mind. I should probably mute my other classes, when I'm teaching this one, because otherwise I get the same kind of notification, but I cannot tell which one it is. All right, so now we get back to B, and kind of the same thing. G of A is 0. We have to add to the distance of the edge AB, which is 3. So here's 3. We compare the 3 with the infinity, which is G of B. 3 is less than infinity, so we have found a shorter path. So it's time to update the g value of b, but we also have to update the f value of b, which in this case is 3 plus the heuristic value from b to x, and that is the only non-zero heuristic value, which is 4. So 3 plus 4 is 7. And to get to vertex B, using this quote-unquote shortest path, we are going from vertex A. So pref is set to A, and then we also have to add B to the set of uppercase O, and that concludes the for each loop, because we have now considered every single outgoing edge from vertex A. So now we get back to the while loop, and the while loop is looking at the set of O, and it's asking, do we have at least one of these elements having a f value that is less than g of x? That's the question. So we have to first find out what is g of x. It's not infinity anymore, it is 10. Now we have to look at the f value of b and c. The f value of b is 7. Okay, that's fine. Okay, we don't even have to look at c at this point, because it only takes one of the elements in O to have a f value that is less than the g value of the destination, to basically say we are not done yet. Okay, so we are now getting into the while loop. And this time, when we try to find a particular element to explore from the set O, it's not as simple as last time anymore, because we do have 3 different elements here, and we have to compare their f value and choose the one that is the most promising. Remember, this is a greedy / optimistic algorithm, so it's just going like, okay, I'm going to look at the vertex that looks the most promising. So when you look at the f value of b, c, and x, the one that looks the most promising is going to be vertex C. So we'll pick that one. And now we have to look at, we have to remove that from the set O, because otherwise we'll end up with an infinite loop. And now we have to, well, not necessarily. Okay, I take that back, because the loop does exit when we do not have any element having a f value that is less than the g value of x. So maybe it's not going to be infinite, but still, I mean, it kind of depends on how we choose things out of it too. All right, so now we look at all the outgoing edges from C, and C only has one single outgoing edge to X. Okay, so not much to choose from in this case. The T value, which is just a local variable, is G of C, which is 5, plus the distance from C to X. The distance from C to X is 3. 5 plus 3 is 8. So we put an 8 here. Now the next question is, we are going to compare this 8 with the current G value of X in this case, which is 10. 8 is less than 10, so that means we have found a shorter path from the start vertex through vertex C. I take it back, sorry. We have found a shorter path from the start vertex to vertex X, and we are not even considering X as a special thing, because we at this point we don't really know nor care which one is our destination vertex. The algorithm in the while loop doesn't care at all whether a particular vertex is a destination or not. I mean, when we look at the variables C and N. Alright, so we're going to have to update this one to 8. And because X is a destination, the heuristic value to the destination is guaranteed to be a 0. So that means the G value and the F value have to be exactly the same. And we have to update the previous, because now that we have found a shorter path from vertex C to the destination, so in order to get to the destination vertex X, we are going through vertex C, so C becomes the previous of the destination. And we are going to have to add vertex X to the set, but it's already here, so it would appear that the set has not changed. But in reality, I try to add vertex X to the set O already. It's just that we cannot have duplicate items in a set. And that's the only outgoing edge. So now we get back up to the while loop, and the while loop has to decide, are we done yet? Well, we have to look at the f value of the vertices or the elements in O and see if at least one of them has an f value that is less than the g value of X. So when choosing our C value, do we have to pick the most promising, meaning lower f value? Alright, do not take me the wrong way, but I'm going to say, what do you think? What does the algorithm tell you? Exactly. So you have to go by the algorithm. So there are two things that are both important. One is the mechanical aspect of how the algorithm is specified. So in the algorithm, it says, okay, pick the one where the f value is less than or equal to everybody else's f value, which is basically saying, okay, we are looking at the minimum, right? That's the mechanical specification of what the algorithm is supposed to do. The translation of that to, in terms of meaning, why are we doing this? What is the rationale of doing this? That is what Elijah just put in the text channel, which is choosing the one that is the most promising. So it's important to understand both aspects and make the association between those two. All right, so we're getting back here. So we look at all the f value of f of x is the same as g of x, so that's not helping us in any way. And then we have vertex b, so f of b is 7. Okay, looks kind of nice, right? So 7 is indeed less than 8. So we are not done yet, because there's at least one element in O where its f value is less than the g value of the destination vertex. So now we have to get back into the while loop, the body of the while loop, and we have to now choose the element that has the least f value. F of b is 7, f of x is 8, so we're going to choose b over here. And then we have to look at all the outgoing edges from vertex b. So when you go through all the outgoing vertices, there's only one outgoing edge from B, which is to vertex C. And we're gonna take a look at that one. Okay, so now we say, okay, vertex B to vertex C. What is the t value? The t value is the g value of B, which is currently a 3, plus the distance of the edge of BC. The edge of BC has a distance of 1, 3 plus 1. Yep, 3 plus 1 is 4. So we now look at the 4 and we ask, is that a shorter path that we just found by going from vertex B to vertex C? Well, we're going to have to do a comparison here. So we're comparing 4 to 3 because we have already found a... Oh, I take it back. Okay, I was comparing to the wrong thing. We have to compare to the g value of C because we found a... This is the length. This is the length of a path from the start vertex through vertex B to vertex C. So we have to compare to the length of the shortest path up to this point to vertex C and not vertex B, which is a 5. So 4 is less than 5. So now we got a bunch of updates again, right? So we have to update the g value and we have to update the f value. So the f value is the g value plus the heuristic going from vertex C to vertex X, and that heuristic value is defined to be 0 here. So that means the g value and the f value are indeed the same. And then we have to update the previous, because we just found a shorter path. Okay, and to be on that shorter path, we go to vertex C from vertex B. So the prev of C becomes B. And we have to remember to kind of add vertex C to the set. So it has X. Oh, I forgot one thing. I forgot to remove B when we chose B from the set O. But now we have to add C back into the set. There we go. All right. Okay. So I want you guys to kind of observe this a little bit because, oh, but Tech, we have this condition already, previously, C was one of the elements in O, and now it is back in O. Is this going to be a problem? Is this going to be an infinite loop? Well, so instead of answering that question at this point, let's try to run the algorithm, see if we can actually get it to end, because that will answer the question right away. It's like, okay, does this automatically lead to an infinite loop? All right, so now what do? We look at the, this is the last iteration of the for each loop. So now we go back to the beginning of the while loop. And the while loop is always trying to say, are we done yet? Can we get out? So now we have to evaluate that again and see if the f value of at least one element in O is less than the g value of our destination vertex. So our destination vertex currently has a g value of 8, and then when you look at the f value of X, it is also 8. But when you look at the f value of C, it is 4. Oh, okay. So it does look promising. So now we remove C again, from set O, and this time I remember to update O so that it is just X by itself. Now we have to look at all the outgoing edges from C, and somebody's gonna say, but we looked at that already. How can this possibly do us any good? Well, we'll figure out, right? That's the whole point of this trace. So now we look at the outgoing edge, one of the outgoing edges if there are multiple from C, and the only outgoing edge from C is going to X, so we put X here, and now we have to compute the t value, which is the g value of C, which is currently a 4, plus the distance of the edge Cx, which is 3. 4 plus 3 is 7, and then we compare this to the g value of from the g value of X, which is 8 at this point. So 7 is indeed less than 8. So now we have found a shorter path to vertex X. So there you go. And there we go. And we also have to update the prev so that we remember, in order to get to vertex X through the shortest path, we have to go through vertex C. That doesn't seem right. because it was a C already. Okay, well, that's fine. So we put a C back here, and then we add vertex X to the set O. It's already here, but that's okay. And that's it. This is the only iteration of the for each loop, and then we are done with the for each loop. So we go back to the while loop, and then we ask the question, are we done yet? Alright, so Nathan asked, we are updating it because C's shortest path changed, so X shortest path also changed as well. Yep, that is the reason. Alright, so now this is the most crucial point of saying, okay, do we understand the condition to get out of the loop? Because right now O is non-empty, right? It does have one element in it, which is X, but we have to see if the F value of the element is less than the G value of the destination, which is also vertex X. So we can look up f of x. F of x is 7 at this point. G of x is also 7 at this point. 7 is not less than 7. So we are done because there are no vertices in O where its f value is less than the G value of the destination. So we are done at this point. All right, so I'm going to pause here, okay, to give you guys a chance to look at the trace and see if you have any questions and or comments. All right, okay, very good. All right, so Elijah said, is there a way to error check my solution? Not the whole trace, but the final answer seems intuitive by looking at the graph and finding the shortest path by hand. Well, I did write the algorithm in JavaScript. I didn't quite check it, okay? This is all done by hand. Well, you guys cannot see my workstation, and I don't have Proctorio running on my workstation. Just having that diagram is not helpful because you need to also look at the H value, because if in this case I specifically designed the H value to mislead the algorithm. It's like, try that. That looks promising. Oh man, that's not the shortest path. Let's try that too. No, that's not the shortest path either. Let's try that one. Okay, okay, now that we don't have any options, let's try that one. That turned out to be the shortest path. So I specifically designed the H value, the heuristic value, playing by the rules, because none of the H value is overestimating, but at the same time, I specifically chose values to trick the A star algorithm to explore something, a little bit more than the more optimized H value. So, so just knowing the graph that Nathan posted is not sufficient to tell us whether the trace is done correctly or not. The only way to tell is really to go through the logic, and really step by step confirm whether we did it right or not. All right. Well, the heuristic value can mislead. Okay, so if you have a good set of heuristic value, you can basically ignore a lot of edges and a lot of vertices and basically go straight to the shortest path. On the other hand, if your heuristic value is designed to trick the A star algorithm, you can make the A star algorithm explore more vertices and edges to kind of get to the shortest path. But it will get to the shortest path. Okay, that is the promise of the A star algorithm, is as long as your heuristic is admissible, which means it is not overestimating, the A star algorithm does guarantee to find the shortest path. The only question is, how much exploring does it take to find the shortest path? If you have, depending on the heuristic value, you can basically guide it straight up to the shortest path, or you can make it go through the scenic route, explore around a little bit before it actually find the shortest path. But it will find the shortest path. That's the correctness part of the A star algorithm. as much as I want to show the proof of the correctness of the A-star algorithm, we simply don't have the time to do that. But the A-star algorithm is correct because as long as the H function is admissible, it will find the shortest path. All right. Elijah said, is there a form of the A-star that explores multiple destinations or start vertices? You can sort of make it that way. You can modify it. You can modify the graph so that you can have multiple destination vertices, and they all have zero distance edges to a fake destination vertex. So that way, the algorithm will find the shortest path to one of the destination vertices. So that's how you can kind of fake the same effect. As far as I know, there are no ways to make it handle multiple start vertices. Or, well, I haven't really put too much time into that thought, but you know, of the 15 minutes or so that I actually spent thinking about this, I could not find an easy way to have multiple start vertices. All right. So we are now done with the assignment. I'm going to wait until Nathan is done typing, and then we're going to transition to the exam, to question number 2 of the exam. Okay, so for example, if this was part of a GPS app and the GPS can factor in traffic information, can we weight a path from a point to the destination with a larger heuristic if there was a traffic accident? You still need to make sure that your heuristic is not overestimating, because it's okay to underestimate but not to overestimate. So in this case, if you do have a traffic accident and it's backing up traffic, you have to find a way to come up with a heuristic value that is not overestimating. So as long as you can do that, the A-star algorithm will still work. I mean, if you give it a heuristic that is potentially overestimating, it will still find a path. It's just it may not be the shortest path, which is probably okay in the case of a GPS app, because as long as the path is still getting to the destination within a reasonable amount of time, it would still not be considered incorrect. So there are things you can fudge, in that sort of application. Besides, if that GPS app is installed on every single car, the moment people, the values are changed, everybody is going to get to the alternative path, which would be shortest for a very short amount of time, and then that path get all jammed up, and it becomes, it's no longer the shortest path, and then the algorithm will now say, oh wait, hold on a second here, there's a traffic jam here, let's try the other path, and then all the cars will try to switch to the other path. So now you have this kind of strange oscillating effect between the alternative paths to a destination. I mean, when people are actually driving, some people are just going to say, well, I know, my way around here. I'm not going to listen to the GPS. But if you have every single car being fully autonomous and they only go by, the shortest path as reported by the GPS, then you have some really interesting, traffic pattern, because you'll see cars, kind of alternating between the different paths, because the moment you change, the shortest path, all the cars would go to that path, and then that path will now become the longer path because every car is over there. So it's oscillation. Yeah, some people pay more for Google services, so those are the preferred customers, I guess. I'm just kidding. I think they do it by just random, so this way, they can distribute the load between the alternative routes, so that we don't jam up one particular route too much. Well, with Google, I think they can look at the political affiliation of people and then send them on different paths too. That would be actually pretty funny. All right. So we are now moving on to the exam, question number 2 of the exam. So for those of you who want to kind of quickly get to the exam, I posted a link at the top of today's text channel that will take you to question 2 directly because I put a bookmark over there. All right, so let's go there. Okay, so it is the final exam, and it's one of those, one of those two. I cannot remember which one. Nope, not this one. This is for CISP440, which is also an interesting final exam, but we have to stay on topic. All right, so here's question number 2 of the exam last semester. Okay, so remember, okay, the focus here is not how we solve this problem specifically. It is not to find the process or to memorize the process of how to solve this problem. It is to find out what technique is being used to solve the problem. Okay, so that is our focus. All right, so I'm going to read the question and bump up the font size, so we can all read a little bit better. There we go. Alright, so you are given the following trace of running the A-star algorithm as described in the module, and it is a link, okay? So for those of you who cannot remember where to find the A-star algorithm, and here's the link, okay? But please do not assume that I will always put in a link to reference material that you may need to answer a question. That is your job, to have your own notes and have your own indexes to find all the relevant material that we have introduced in this class. Okay, so which also means if somebody texts me and go like, I cannot remember where to find the algorithm of A star, I cannot answer that question. Okay, because that is kind of your job. Okay, to kind of index everything so you know where to find it. And discuss this in class. The initialization is not included in this trace. As much as possible, reconstruct the original graph. So this part here is consistent with what Chris said in a previous class, that you cannot always reconstruct the original graph because the trace may not give you enough information of the edges and vertices that did not get explored. Okay, so I'm just going to say as much as possible. Reconstruct the original graph, G being having V as a set of vertices, E having being a set of edges, the edge distance function D, and the heuristic function. So you have to reconstruct all of these things. Note that a solution may not be unique, so that means there may be multiple ways to make this happen. You just have to find one way to make this happen. You may assume the destination is vertex V5 in this case, so just kind of make note that this is the destination. Be sure to explain along the trace how you determine elements of the sets as determined in the previous paragraph. In other words, tell me why you think this is one of the vertices. Tell me why you think this is one of the edges, and so on and so forth. Now, obviously, you might be reusing the same explanation over and over again, because there's a pattern to it. So you can give your explanation a number, some kind of identifier, and you can just say C blah blah. Okay, so you can give me a pointer. Okay, or for those of you who are Java programmers, you can give me a reference to something that you have already mentioned earlier. Answers without explanation will not receive any points. Okay, so I'm not asking you to just give me the final answer. I'm asking you to tell me how you solve the problem. Okay, so explanation is a key of this type of a question. Well, you may draw a graphical graph on paper and scan and include it in the answer. Your deduction must be typed in this document along with the trace. So you're going to have to explain it in text, okay, and not just give me a graph and use that as quote-unquote the explanation. Use comment style to state your reasoning. For example, obviously not directly relevant to this question because this is using an L value, and L values are not used at all in A star, but I'm just using this as an example. So if this is part of the trace, you can now say, okay, as an explanation, L of A is L of C plus D of CA, L of C is 2, and hence D of CA is 7 minus 2, which is 5. So that's the kind of explanation, the format of the explanation that I'm expecting. Okay, now obviously this does not apply directly to the A star algorithm. So with the A star algorithm, make appropriate adjustments. Okay. To help shorten your writing time, you can use the following abbreviation to specify the length of a path. So instead of saying the length of a path is the distance of an edge plus the distance of an edge plus the distance of another edge here, you can just say, PL, which is path length of going from VA, V1 to V2 to V3 to V4. So that way you can save quite a bit of time because you don't have to type out the summation of the distance of the edges, because you just use the shorthand. The following is an actual trace with certain values replaced by question mark, question mark, question mark. Equal equal is confirmation of equality, whereas equal means assignment. So these are all the symbols that I use in the trace. Updating the left-hand side to the value of the right-hand side. So this is assignment. It's basically the same as an assignment operator in C and Java. You evaluate the right-hand side, you change the left-hand side to whatever the right-hand side is. Present the final answer at the end of the trace. Show the values of V, E, D, and H that is consistent with the trace. Okay, so the key here is it has to be consistent with the trace, which also kind of implies that it may not be a unique solution. There may be multiple different ways to come up with a consistent D and H function to do this. Before you determine the exact function D and H, which basically are sets of tuples, you may want to log, explain, and list a set of equalities and inequalities, okay, inferred by the trace. So I'll get to that part. I'll explain why this sentence is here. Note that there can be many possible alternative answers. Your answer just needs to be consistent. Okay, I'm repeating myself here, not knowing that I became a broken record. Note that a verification of the values is not considered an answer with reasoning and deduction. This is really important because in past semesters, there are people who do that. Okay, people who just say, okay, this is V, this is E, this is D, and this is H, and by going through the algorithm, this is consistent. That is not an explanation of how that person came up with the D and the H values. Okay, it simply means given these D and H values, it is consistent with the behavior of the log. And it's not the same thing. Okay, they are not the same thing. As an exception to the rule of no copy and paste, you may include a graphical representation of the graph if a visual graph is easier for you to work with. So this one is not you don't have to include it, okay? Because obviously I know what the graph is supposed to look like, because I came up with these questions. So the graph, you can just kind of jot it down, on the side, and you don't have to include it as a part of your answer. But if you feel like it is helpful to be a part of the answer, you can do that as well. This can be used to answer up the part of V and E. So you can basically say, okay, here's a graph, and there are these vertices and they are connected by these edges. So what this part means is, it can be the final answer of what V and E consist of. But it does not meet the requirement of the explaining of why you think certain vertices and certain edges are in the graph. The reasoning of D and H should be written in this Google Doc, which means you're going to just have to type within the Google document. However, note that you may need to experiment with values a little bit, and it's okay to change the D and the H function a few times in Google Doc. Alright, so let's go ahead and start with the trace. So the first line here is simply saying O is a set with V1 as the only element in it. Okay, this is the first. This is the beginning of the trace. Okay, and what is this telling you? Is this line important all by itself? And if so, how is it important? What are you going to say? What are you going to explain and go like? Okay, so we can write a few things about this. So the first part has to do with how do we initialize the set O, right? So what is the first element, the only element that we put into O before we get into the while loop? Nope, nope. Okay, yes, yes. Okay, so Marco and Nathan are both correct. This is the start vertex. Okay, V1 is the start vertex because of how O is initialized. Okay, so that means we also know that V1 is in the set of V. Alright, so I'm gonna change the page layout a little bit so I can have wider and more stuff for the comment, or you can choose a smaller font. But I think it's easier to change the orientation. So we'll change the orientation to landscape, and that should update on your side as well. Alright, there we go. Alright, so the next line, which means we are choosing v1 to be variable c, as indicated in the algorithm. This one doesn't tell as much, right? Because as the only element in O, that's going to be the one. The fact that we get into the while loop also means v1 has a f value that is less than the g value of the destination. But at this point of time, that is also of little significance because the g value of the destination is infinity. And the fact that v1 is in O means that it has a non-infinity f value. So that by itself is not really particularly helpful to us. The next line is not helpful because this is simply saying that once we have chosen an element to explore out of O, we remove it from O. So there's really not much to say about this. Now this one is important. Okay, so there are a few things you should write about this. At least one right now at this point. So what do you think that is? What is the significance of this line of the trace? How do we get to determine the value of variable n? V2 is a neighbor. Very good. Okay, but not only a neighbor. Luke's answer is a little bit more complete because a neighbor doesn't quite tell you, which one goes to which one. And what Luke, presented in the text channel says two things. Okay, because now we know V2 is in V, and we also know that V1, V2 is in E. It is an edge. Does that make sense to you? Because in the algorithm, we are exploring all the outgoing edges from whatever C, the variable C is containing. So the fact that we are now instantiating variable n to be V2 basically says, yes, there is an edge V1 to V2. All right, cool. All right, so this part here is saying we don't know what t is. Well, we know in terms of equation what t is supposed to be. Okay, so we can say, now that we know what variable c and variable n are, we can now say, symbolically we can say t is g of c plus the distance from c to n. But these are referring to the names of the variables. But we know a little bit better, right? Because we can now actually say, oh, but since we know what c is, we know it is g of v1 plus the distance from v1 to v2. But we also know that v1 is the start vertex because of the argument that we have already presented here. So now we can say, okay, if it's the start vertex, the g value is going to be a 0. So we just boil this all the way down to the distance between v1 and v2. Okay. Now, why is this important? Because the next line says we're going to do something about the set O, the value of G, the value of the G value, the F value, and the pref value of V2. What is that telling you? How do we get to that point? In other words, the fact that we are doing these 4 lines, what is the significance of that? you have to look at the algorithm, because you have to basically say if we are here, that means this condition has to be true. Exactly. Okay, very good. So Elijah is correct. Okay. Now in this particular case, it doesn't seem to give you a whole lot of information, but it is a pattern. Okay, because I'm trying to describe the technique. So you have to go to the algorithm and say, if I'm in this part of the program, and that part of the program turns out to be the then branch of a conditional statement, it means the condition of the conditional statement has to be true. So this is how we can say, okay, so we can now infer a few things, right? We can infer that t, which is just the distance between v1 and v2, is less than the g value of v2. But we also know that other than the start vertex, every other vertex starts with a g value of infinity. So that by itself says, okay, we're back to square one, because it's not really super duper helpful to say that the distance between of the edge v1 and v2 is less than infinity. That's not helpful, okay? But it is the technique of understanding that at this point we can confirm this. That is important, okay? All right. So now we know g of v is updated to t. So at this point, we say g of v2 is the distance between v1 and v2. Okay, and now that is important, right? Because it says the because how do we come up with the f value? Okay, the f value is the g value plus the heuristic value between the vertex v2 in this case and the destination. And we already know what the destination is. It is part of the description of the question, and I need to go find it. v5, there we go. Okay, so this is telling us that f of v2, which is g of v2, g of v2 plus the heuristic of going from v2 to v5 is 13. Okay, that's what this is telling us. The next line is not super duper helpful because it simply means we have a way to trace back how to get to v2. So it's not really that particular valuable to us. Okay, so let me get to the text channel. F of v2 is g of v2 plus h of v2 v5. Yep, that is correct, and that's exactly what I typed. So now we know that g of v2 is less than 13. Yep. Yep, exactly. So you can also add that. Not sure whether that's going to be helpful or not, but we can always kind of add it here. So g of v2 is less than or equal to 13. Okay, that might come in handy. It may not. All right. So next, we have n being v6 as another neighbor. So now we can say that v6 is in v, and v1, because c is still v1, so v1 v6 is in e. So as you go through this, it might be more helpful to change this representation and basically say, v2 is a subset of v, and you can also now say v1 v2 is a subset of e. Now, the reason why this might be a more handy way to write this is because you can keep adding more elements to this, blah, blah, blah is a subset of. So this way, you have I would just call this a running sum, of the values. So this way you don't kind of, at the end, you lose track of things. So, so I'm going to change the representation here, just so that it's easier to see it. So v2, v6 is a subset of v. And I'm going to use bad grammar here, subset v, and over here we have v1, v2, comma v1, v6 subset of e, just so that I don't have to type as much. There we go. All right, so given the pattern that we have seen so far, we know that eventually we got in here, but what is the t value? So in this case, we can say the t value is g of v1 plus d of v1 v6. And the fact that we got here is because this t is less than g of v6. But that by itself is not very helpful because, because v6 currently has a g value of infinity. But noticing the pattern, is helpful because at some point, v6 is, the g value on the right hand side is not going to be infinity. But right now, it is infinity because we're at the very beginning of the algorithm. And at this point, g of v6 is g of v1 plus the d of v1 v6. So this is important because you want to kind of keep track of what the g value is at a certain point, because later on, if we refer back to g of v6, we know how to spell that out. Okay, so that's important. And then f of v6 is 3. Okay, that's certainly helpful because now we know g of v6 plus h of v6 to v5 is exactly 3, which also tells us that g of v6 is less than or equal to 3. So are we good so far? Are there any questions about all these rationale and explanation of what we have found out for all of these lines that are commented? Okay, no questions. All right, so moving on. All right, so this part is kind of useful, but it's not super duper useful because the fact that we are choosing C instead of the fact that we are choosing V6 instead of V2 is pretty clear, okay? Because we know that the f value of V6 right now is 3. We know the f value of V2 is 13 at this point, so it kind of goes without saying that V6 has a smaller f value, and that's the reason why we choose V6 to be C in this case. So I don't really feel like it's telling us much at this point. But this line does give us some additional information. All right, so Nathan says it's just confirming that what we already know. Exactly. Now, if this part here is conflicting with what you already have worked out up to that point, that means you might have made a mistake earlier. Okay, so you might need to go back and check on things. But right now, everything seems to be consistent. All right, so just knowing that n is v3 is now telling us that v has, and this is the nice thing of using an editor because you can just kind of copy and paste. So I would just kind of look at this entire line here, copy, paste, and then just add a few things to it. All right, so at this point, we know v2, v6, v3 are in the set of V, and we also know that v6 and v2, v6, v3 is an edge. v6, v3 is an edge. All right, there we go. And t is, so if you just kind of look at this format here, based on what is c, what is in the variable c, and what is in the variable n, that's basically just a template, right? So in this case, t is g of whatever c is, which is v6 in this case, plus the distance between v6 and the neighbor v3. We don't know exactly what it is, but we just know that that t is less than the g value of v3 because we got to the then portion of the conditional statement. So right now, the fact that we got into the conditional statement is not telling us much because this is the first time we see v3, which means the g value of v3 is infinity right now, and just knowing that t is less than infinity, that's not really super duper helpful to us. So we'll just kind of ignore that and say, not much about it. But we do want to remember that g of v3 is what this t is. So I would just kind of copy and paste. And by the way, copying and pasting within the document itself is definitely allowed. So that's how you can save some time. And then this part here, it's the same reasoning, okay? So we basically say g of v3 plus the heuristic of going from v3 to v5 because we have v5 as our destination. So this is exactly 14, but it's also telling us that g of v3 is less than or equal to 14. And updating the previous is not really helpful to us, because that's just telling us how to get back, but it doesn't, which we can already figure out by looking at the edges. So there we go. All right, so now out of the two vertices v2 and v3, we choose v2 as the one to explore. Well, that's not really surprising because we already know what is f of v3. It is 14, and f of v2 was determined earlier, which is also 13. Oh, one is 13 and the other one is 14, sorry. So this one is 14, the other one is 13, so we choose the one that is less. So the behavior or what is logged here is consistent with what we have already confirmed. So there's really not much to say unless you just want to say confirmed, okay? You can always say that if you want to. So this is confirming f of v2 is less than or equal to f of v3. Okay, so it's not necessary, but you can always put it here. And now that we have done that, we are now looking at the neighbor of v9 coming from v2. So so same format. Okay, so this is why copy, paste, and modify is kind of handy because we are just adding to the set of v and the set of e as we go along. So this part is the easy part, right? Because now we just say, okay, here's one more vertex, and here is one more edge. The edge is always going from v2 or whatever is in variable c to whatever is in variable n. In this case, it's v9. And then the t value, once again, not mysterious. T is just the g value of v2 plus the distance of v2, v9. There we go. All right, we add it to O. Okay, not super duper important. G of v9 is just whatever t has, but don't say t, okay? Because t is a local variable, it's temporary. So you want to express all the g values in terms of g values of other things. So this is where the shorthand can come in handy, okay? Because what do we know about g of v2? So g of v2 is the distance from v1 to v2, and v1 is our starting point. So it's v1, v2, v9. So using the shorthand, this is PL of v1, v2, v9. So this way, it's just a notation that's easier to type. You don't have to, and it goes all the way back. So this is kind of important, and we'll see why this is important in just a little bit. Okay, so now we have PL v1, v2, v9 plus the heuristic from v9 to v5 being exactly 15, which is also telling us the path length from v1 to v2 to v9 is less than or equal to 15. There we go. And I'm going to go back, to kind of back change this one because v3 is not the start vertex. So that means, v3 itself, is coming from v6, and v6 is coming from v2. So I want to re-express, all the g values as a PL of some kind. So that means, I kind of have to go back a little bit. G of v2 is that distance, which is actually just PL v1, v2. And every time I refer to G of v2, I should replace it with PL of v1, v2. And then we have v2, v6. Oh, did I? No, that's fine. Okay, so that is just PL V1 V6. There we go. And then we refer to G of V3, and this is the first time V3 is mentioned, so we don't have to, it cannot be defined by other things right now. But V6 is not new, so V6 is already defined here. So this is PL V1 V6 and then V3. Okay, so that part is kind of important because as we go along, we'll find out that the summation is really kind of, oh, okay, I think I just, oh, no, V3 right there. So this one, I'm going to replace this G of V3 with PL V1 V6 V3 like so. And this is PL V1 V6 V3, because we want to be able to spell out how we get to a specific G value, because that is how we can relate which one is larger, which one is smaller, and so on. So that will become important in the next part. All right, so so that's it, and now we start with V9, because V9 has an F value of 15, and then V3 has a F value of what? Of, oh, wait, that doesn't look right to me. V3 has a F value of 14, and then V9 has a F value of 15. Oh, wait, okay, never mind. Okay, never mind. Brain fart here, because C is the one where this is okay. We choose that because V3 has a smaller F value, so that is okay. That's fine. All right, so get to this point here means we now know more about the vertices. So we're just stacking on this comment here, and at some point it's going to be a multi-line kind of comment. So we get it to here and paste that. And because now we know V2 is already in V, so that part we don't modify, but the edge is new to us. So we now know that V3 going to V2 is a new edge. V3 is already here in the set of V. V2 is already here in the set of V. So V is not changed. Okay, what we know about V has not changed, but what we know about E has changed. And right here we say G. This is T is G of V2, and we want to look up what is G of V2 right now. So on the side, you can use whatever way you want to do this, but it's kind of tedious that I have to go back and forth to look up what is in what is G of V2. So G of V2 is PLV1 V2, and right. So this is PL V1 V2 because that is how G of V2 is defined at this point. Which is the length of the path from V1 to V2, and we have to add the distance of V2 to V. Nope. Okay, I take it back. Keep on brain farting because we are looking at V3 here, so we have to look up the G of V3, and G of V3 is defined here. It is V1, V6, V3. So this is how we define G of V3. All right, there we go. And we add the edge from V3 back to V2. So this is basically, the other way to express the same thing is this is PL, or path length, of V1 to V6 to V3 to V2. And the fact that we are now in the conditional part means this PL is less than whatever G of V2 is. So now we can conclude PL V1, V6, V3, V2 is less than whatever G of V2 is at this point. So G of V2, let's see, where's G of V2? All right, there we go. So G of V2 is PL V1, V2. So this is less than PL V1, V2. There we go. All right, so let me get back to that is a I do not know, because I'm explaining along the way too. So when you guys are answering the question, you don't have to verbally answer that. Explain it to me too. Plus, there are 2 hours, right, for all the questions. Right. Okay. So getting back to here. So G of V2 is now updated, and it is PL of V1, V6, V3, V2. So now this is important because right now we are changing how G of V2 is defined. Now there are probably better ways to track this. Like you keep track of all of the G and all the F values, as you go along. So that way you don't have to trace back, to find out how something is defined. So right here we say G F of V2 is PL V1, V6, V3, V2 plus the heuristic from V2 to V5, and that is exactly 9, which is also telling you that PL V1, V6, V3, V2 is less than or equal to 9. And moving along, so this time we chose V2 to expand, and it goes to V9. So once again, we are copy and pasting to discover, because we discovered a new edge, maybe. Okay, so it does not necessarily mean that we have discovered a new edge. So when you add the edge to E, you kind of have to double check. Okay. All right. So V2, V9 are in V already. The edge V2, V9 is also in the set already. So we are not adding any new edges here. But the fact that we are getting into the else statement means that we found a shorter path. So when we find a shorter path, it means PL of how we get to V2. So the way we get to V2 is V1, V6, V3, V2. So V1, V6, V3, V2. Plus the extra one, which is V9, is less than the PL of V9 from before. So we have to look up what is G of V9. So G of V9 is this right now. So we copy and paste that because we found a shorter path. So this is the crucial part, because this allows us to compare the path length between these alternatives. And when all of these are done, when they're all figured out, you will find that you can form, depending on the ordering, okay, you can then work out the values of the distances of the edges. I do realize that we are running out of time today. We are now at 1:23. So I'm not sure whether you guys want me to continue to work on this, or do you want me to work on this and you guys kind of just sign off, then I can give you the answer. The key, I think, is already disclosed, so you can actually practice now that I have shown you the technique to do this. So do you guys want to do that, or do you want me to kind of keep going? I have to go back to take a look at the grading of the final exam. The question alone would take an hour maybe. Not sure. So if you guys want to, we can go ahead and just keep doing this. Six V2 V2 V9. I mean, we are pretty close to the end. So there we go. All right, so this is the first time we see V4. So V4 is going to be added to the set of V. Along with the edge ending at V4. And the edge ending at V4 is starting from V9. So we are adding an edge from V9 to V4. Like so. And because this is the first time, it's guaranteed that we have found a shorter path because every vertex starts with infinity as the G value. So G of V4 is basically the PL of however way we lead to V9, which is from the previous one. So we take this path length, stash it here, and just add V4 to the path. And now we can say PL. Okay, copy and paste whenever possible. Copy, paste, plus the heuristic from V4 to V5 is exactly 14, which is also telling us that this path length is less than or equal to 14. There we go. Alright, so this is the last iteration, which is from V4 to V5. And it's also the first time V5 is mentioned. So we update. Oh, I pasted this at the wrong place. Okay, but that's okay. And the edge that we are adding is from V4 to V5. There we go. The G value of V5 is from V4, so we got G of V4 being this path length. And we have to add V5 to the end of this. So there we go. And that is also 14. The F value is also 14. So we say this. And V5 is special. Remember, V5 is our destination. So we can now say, this path length is in fact 14 because h of V5 to V5 is guaranteed to be a 0. All right. And then the algorithm exit, when V5 is the only element left, because the F value of an element cannot be less than the G value of the same element, and V5 is the destination. So that's why we exit at this point. All right, so at this point, we have a bunch of comparisons. So we have some. So this is where partial ordering comes in handy. This is another way to kind of explain partial ordering, because we are looking at the ordering where it is not complete. Okay, so you can't really say exactly the path length, how they are totally ordered. It is partially ordered, but addition to being partially ordered, you also know, this path here, this entire path length is exactly 14. And if you remove the v5, the heuristic gives us, that it is also 14. So that tells you the heuristic between v4 and v5 is exactly the distance from v4 to v5. So that is kind of, the reasoning that you have to apply to get back to the distances between, the vertices, and also the heuristic value to the destination vertex. All right. So if you take, all of these comparisons, okay, if you take all of the PL comparisons and kind of stash it at one single place, then you'll get a better view of, how they compare. Let's see. So we take this one, okay, and we've just put all of those comparisons to the end of the trace. So we have a conclusion of all of these things. So this is where, if you draw a graph, that might be helpful, but I don't really have a graph with me. So I'm just working on this symbolically. Oh, we got that one already. Okay, so this is a less than PL of V1, V2. It's harder for me to kind of track where I have copied and pasted. Okay, I think it's from this one. So what I'm doing here is I'm just collecting all of those partial results that I got from earlier. And let's see, we got a 14, 14. Here's an 11 that I have not captured. Yep, that one is not captured yet. All right. And about the 15, did I capture that? Nope. All right, so this is basically, just a process of, capturing all of this stuff here. If you open up another window, it is a whole lot easier because you don't have to go all the back and forth, because you can just kind of sequentially go down the list and paste it to the other end. I'm only using one window here, and that does make it harder. All right. All right, so what we can see here is the single edge of from V1 to V2 has a large value, and is larger than the value from V1 to V6 to V3 and then back to V2. And then this particular subpath here, v1, v6, v3, v2, is repeated in all of these paths here. So that means the individual values of these edges are not as important as the fact that when you add up these four edges, three edges, sorry, there are three edges here. The combined distance or the length of the path has to be less than the edge from v1 to v2. And so that part is important. We also know that this plus v of the heuristic value from v2 to v5 is 9, and that is telling us that v1 pl v1 v6 v3 v2 is less than or equal to 9. So anything less than or equal to 9 can meet this requirement, but it also depends on how we want to figure out the heuristic value from b2 to v5. All right, so let's go ahead and work out some values here. And this is where having an actual graph is helpful because it's more intuitive. You can actually look at the edges and the distances and go like, okay, so this has to be a larger value, and you want to know how large it can go. And I think there is a particular value we can look at. I probably did not copy that, because when we worked out v2, it has a f of v2 has a value of 13, so that means it has to be less than or equal to 13 here. So this value has to be less than or equal to 13. We also know the final path, the final shortest path, has a length of 14. So that this part is important too, because now we know this is the length of the shortest path. So we know this is exact. And I'm not sure whether that was captured down here. Yep, it was. All right, so well, without looking at the graph, it's a little bit harder. We can tell that this is less than that, and this is 9. So this has to be less than or equal to 9. All right, so we say, what if PL of V1, V6, V3, V2 is exactly 9? If that is exactly 9, then how do we get to the 15? Alright, so where's the PL with V5 as the last item? I did not capture that. I did, but it's out of order. Alright, so if this is 9, that means this portion is a 9. So these other 3 items, they have to add up to 14 minus 9, which is a 5. So we need PL, let's see, V2, V9, V4, V5 to be exactly 5. Alright, without drawing a graph, it's really hard. But once you have a graph of the connectivity between the edges, it does get a whole lot easier because you can actually more intuitively see how the edges are kind of connected and how you can form a sub portion of the graph. So I can't really I cannot finish this without a visual of how the edges are drawn. So I'm gonna have to stop here because I don't have a way to capture the actual graph. So I can capture the actual graph and then post the answer based on the analysis of the visual graph. All right. So are there any questions about this one? I think so. I think there's a key for this one. Um, the key gives you all the ordering. It doesn't give you the actual value. Let me look for that. Did I give you the key to this entire exam? I thought I did that, but I could have might not have done that. Did I do that? I think I did. Mm, okay, so let me. Yep, it is. I think it's also in the general text channel. Let me check what is in the text channel. There's a PDF in the general text channel that has the name of FXK, which is final exam key. Yep, that's the one in the general channel. In the general text channel, so it gives you. It doesn't use the P. Wait. Okay, it is. Okay, so let me show you what the PDF has. Oh, okay, that's not helpful. Um, hmm. Oh, I know how to do this. Maybe. Yeah, so if you go to the general channel and look up the file over there with the name of FXK-W00068887, which I think is the last post in the general text channel. It does have a key, and the key. Okay, I can show you a part of it because. Well, let me change the PDF reader so it doesn't automatically zoom to fit. And let's see, fit to width. There we go. All right. So it does capture about the same thing. It says at which point we know what vertex is in the set V, which edge is also going to be in the graph. It figures out how the relationship. So PL is basically L here in this notation. So at the end we end up with what we know about the ordering of these things. And that's the conclusion from the key generator. The exact value just has to kind of make this work. Okay, so whatever value you choose for the distances between the edges just has to make all of these constraints work. Is that okay? And this is the key, because depending on how people work out the values, it may not be a unique answer. And if there's no unique answer, I can't really generate specific values. So this is how my key generator gives me the constraints. So I'm just looking for whether the constraints are satisfied or not. All right. Okay, so we are out of time, but at least we went over all 4 questions from the previous semester. I will try to factor in how much time it takes to kind of type and write out the elements. So and the format of the questions I have not decided yet. But one thing that you can count on is it will require you to understand the material and understand the algorithm. So the technique that I use, I know this takes a long time, but the important part is, do you understand how I reason out all the individual items? This is a collection of all the individual items, but as I go through the trays, do you understand how I can add certain things to the subset of V and the subset of E? Do you understand how I can determine what G of V4 is at this point? It is the length of the path from V1 to V6 to V3 to V2 back to V9 and then to V4. So how is that determined? And more importantly, how do we determine the ordering? In other words, how do I come to the conclusion that the length of the path from V1 to V6 to V3 to V2 to V9 is less than the length of the path from V1 to V2 to V9? So those are the more important part, is how do we use the algorithm and use whatever the trace is providing to conclude certain things about, as much as possible, to conclude something about the original graph. And I think that is the most important part. Most important part is how is that done. Now this time we're doing it to the A-star algorithm, but we can apply this to the Dijkstra's algorithm as well. Looking at the trace, just because we are at a certain point of the algorithm implies that certain things have to be true. Like a certain edge has to exist, a certain value has to be less than another value, and so on. So we are using those to help us piece the whole thing back together. So is that part okay? Because I think that part is actually the most important part, because it's not about this specific question and about A-star specifically. It is more about how do you read the algorithm, look at the trace, and then use the algorithm to help you infer what has to be true at a certain part of running the algorithm. So I want to make sure that that part is understood. All right, cool. All right, so I'm gonna stop the lecture now. All right, so I'm gonna stop the lecture now, and I'll work out a systematic way to find the actual find values that will make this work. Because the way I did this manually is really just look at the graph and then just assign values, and kind of make sure that I meet all the constraints. So it's kind of more of a trial and error type of approach, and I will try to work out a much more systematic way to do just that, and that's it. Okay, so between now and the final exam, I do have office hours. So let's just say make the office hour from 9 to 10 each morning. So that way, if you do have any questions, you can, get to my quote-unquote office hour by Discord. It's not like I'm not going to answer questions otherwise, but during the office hour, I can be guaranteed to be here and I can talk to you guys. Yep, 9 to 10. Yep. Let me put it into the general channel so this way people know where to find it. There we go. All right, so that's it. And if I find out if I have any additional advice of how to prepare for the exam, I will try to post as much as I can. But thoroughly understanding the algorithm in the case of A-star and Dijkstra's algorithm, that's one. In terms of the probability stuff, thoroughly understanding when to apply which way to calculate probability is going to be the important part. Okay, and I believe that I already gave you guys a kind of decision tree. So we first look at with versus without replacement. If it is without replacement, then we look into whether it is combination versus permutation. If it is with replacement, then we have this special case of if every single trial has exactly two outcomes, it's going to be a binomial type of distribution. And if it is not not two outcomes per trial, then we have a much more general thing where we just use the power function to calculate the number of possible outcomes. And then with combinations, we have the special cases of the lotto game. Okay, so the lotto game is one of the most important concept, because if we are choosing five numbers, we're choosing five winning numbers out of 69 possible. Oh, sorry about that. I'm gonna ignore that one. So out of 69, we are choosing five. But the tickets, okay, so the first part is how many possible tickets do we have. In this case, the Powerball is kind of throwing an extra thing into it because the Powerball number is not a part of the five winning numbers, so it's just multiplied by 26, and that's on its own. But when you look at a ticket and you say, okay, but I want to win a specific prize where I have three of the winning numbers and two of the non-winning numbers, then you have to choose the three winning numbers from the five chosen winning numbers, and then you have to choose the two non-winning numbers from the rest of the 69 numbers. So that pattern is basically repeated, in the exam question. The one that we worked on, where you have two different trick coins in your pocket. Okay, that one is coming from even an earlier semester, but it does illustrate how to analyze the problem. Which portion is a combination versus permutation kind of problem? Which part is a binomial type of distribution? So the one thing about binomial distribution is you can have a asymmetric distribution of probability between the two possible outcomes per trial. So in the case of a coin toss, you can have a loaded coin where landing on the head versus landing on the tail may have a slightly different probability. If you want to look at the extreme version of this, then you're looking at the transmission of bits, right? Because the chances of transmitting a bit correctly is going to be pretty high compared to the chances of not transmitting a bit correctly. But nonetheless, it is still two possible outcomes per trial. And in those cases, we apply the binomial distribution. So when you apply the binomial distribution, then you have to figure out, how many to choose from and how many am I choosing? What is the probability of landing, quote unquote, on the head, which can also be other things, and what is the other probability, which is just 1 minus the first probability. And then the other part is, how do we combine different types of categories? So if you remember in our packet transmission example, if I ask, okay, so what is the probability that the packet is beyond repair? That means you have to add up 0 error bits, 1 error bit, 2 error bits, and then 3 error bits, because the packet can self-correct up to 3 error bits. So you have to figure out what probability to combine depending on what the question itself is asking. So this is a quick summary of of that stuff. So you basically have two main types of material. One has to do with probability distribution. The other one has to do with the graph algorithms. It can be Dijkstra's algorithm, can be the A-star algorithm. And that's about it. I mean, that's about the scope of the final exam. Quantified expressions are still important because that is how the algorithms are specified. So that part is important. Understanding the omega function versus the U function, because those two are being used to generate the actual set of outcomes. I would say that is important in its own way because it is basically a specification of how do you generate all the permutations and all the combinations. So I would say that is important as well. So out of my head, I can't really say much more, just because, I think I have just quickly gone over the scope of the final exam, along with giving you some tips of, what to study. It's basically about categorization, matching patterns, and understanding um, the concepts and specifications in the course. So that's it. That is that. All right. All right. So I am going to get out of the text channel. And as I said, if you guys have any further questions, contact me by direct message, and I will try to get back to you as soon as possible. All right. Um, Okay, so Danny posted something in the general text channel on Monday only. Nope, it is on every single day. So starting tomorrow is our first. Oh, tomorrow is going to be a tricky one because I'll be driving at about 9 a.m. So I'll get back to you guys as soon as possible. Let's change that to 8. Okay, so tomorrow we can change it to an earlier time. Okay, so from 8 to 9 tomorrow, and then from 9 to 10 on days after. There we go. All right, so no problem, not a problem, but I do want to kind of get the main point across, okay, which is not to study and not to perfect the process, but to understand the techniques that was used today to figure out, these things, and which is basically by looking at the algorithm, understanding the algorithm, and relating the trace or log to the algorithm. That really is the important part of today's lecture. The rest is kind of just tedious. All right, so I'm gonna get out of the live share and the live stream now. All right, you guys have a nice weekend. Please study, but study in a productive way. Okay, I'm gonna emphasize that. All right, so I'm gonna get out.